Hello, everyone. My name is Zhu Qiao. We are Group 4I, and we'll be presenting our project, which focus on hardware acceleration for generating the Mandlebrot set images. So first, what is a Mandlebrot set? It is a famous factor defined by an iterative equation that's shown over here, where C is a complex number. Each point in the Mandlebrot set is determined by applying this equation over and over again to a given complex number. I'll go into detailed calculation process for a single pixel point on the next slide. But before that, you might wonder, why are we interested in calculating this for the project? So for generating high-resolution Mandlebrot images is computationally expensive because each pixel may require thousands of iterations to determine whether it belongs to a set or not. So our project demonstrates how to use a hardware accelerator to handle this work. And also the image on the right is an example image generated from our design. So moving to the next slide, let's consider a specific example. Suppose we have a complex number with a real part of -1 and an imaginary part of 0.5, as shown in the figure over here. Applying the Mandlebrot equation iteratively, we can generate the corresponding z-values as shown in the table over here. So as the number of iterations increases, the z-value either converge or diverge. The Mandlebrot set includes all points of C where value converge to a boundary, and we assign different color for them. In our project, we divide the coordinate into 200 rows to 300 columns of pixels. Due to the symmetry of Mandlebrot set, along with the real axis, we only need to calculate half the point, which still amounts to 30,000 pixel points. Each point requires up to 1,000 iterations, which making the total computation really resource intensive. That's why hardware acceleration is really critical for this project. In this slide, I'll explain why parallelism is essential. So each pixel calculation is independent to each other, making it an ideal candidate for parallel processing. We choose to use an FPGA because it can be configured to implement highly parallel architectures. Using Vivado, we're able to bring this design to life.
The baseline implementation consisted of three different stages. The first stage being the compute stage. In the compute stage, we calculate all the necessary Mandelbrot computations. We used a separation of imaginary value and real value calculations. This was done so that we could further helped us in of the optimization part of the algorithm. Next, there's a convergence check. For a pixel to be a part of Mandelbrot set, its magnitude should be less than 2 for given iterations. Instead of having the magnitude, we used the magnitude square equation. This helped us in reducing the computational overhead by not calculating the square root. The convergence check tells us whether a pixel has diverged or converged. Also, it tells if the pixel has converged, it tells us the amount of iterations in which it has converged. Then the final stage is the mapping stage. In the mapping stage, we map the count to different color groups. We have divided the max iterations into 9 different color groups. 0 indicating black and 8 indicating blue, and so on. 0 states that a pixel has diverged for the given iteration, while 8 indicates it has converged in the fastest possible iterations, that is the least amount of iterations. So as we move from left towards the right, the convergence is faster. Next, let's look at the base loop order. Loop order is the most important part for any parallel algorithm. Since we know that Mandelbrot set has a temporal dependency. That is, the current iteration depends on the previous iteration. To maintain this temporal dependency, we use the following group order. The count was the outermost loop, followed by rows and columns. But this does come with a trade-off. We have to save the state of the whole grid for every iteration. So we use three different arrays: a position set array, a Z-real array, and an imaginary array. The position set array helps us to check whether a given pixel has converged within the given iterations. If it happens, we don't have to calculate the further computation, and this does reduce our overhead. While the Z-real and Z-imaginary store the real and imaginary part for the given iterations. So there's this interesting observation over here. We are not storing the whole grid. Rather, we are just storing the half of the grid. Just why? So we came up with the interesting observation that Mandelbrot set is symmetric about the x-axis. So we don't actually have to store the whole grid. We can just calculate the half of the grid and then mirror it. which produces the optimum results.
We initially picked a data type that we knew would be overkill for our design. This allowed us to focus solely on getting a working implementation without worrying about weird issues due to overflow or not enough precision. Once our baseline design was working as expected, we moved on to exploring other fixed point sizes. This image on the left shows our output with our initial fixed point type of 37 total bits with 5 integer bits. We found that many other sizes also produced the same output, but the smallest size that produced this was 25 total bits with 5 integer bits, and we settled on this for our design. During this exploration, we produced a couple of interesting images. This middle image looks generally correct, but the line extending out from the left disappeared due to not enough precision. You can see in this middle image, there's not a really defined line here. And on this leftmost image, there's a pretty clearly defined line. The rightmost image obviously has some issues. This is due to overflow. Our design checks against a magnitude of four divergence, and just 2 integer bits cannot represent that large of a number.
In an attempt to optimize our design, we exploited intra-tile parallelism for Mandlebrot computation. This involved breaking the subspace into a series of tiles with dimension tile row and tile column. In this specific example, each tile would need to process tile row times tile col elements, which in this case is 12. We then pipeline the computation of these tiles across the column axis, which unrolls the computation inside the loop. In this example, we see how the compute for each tile is processed in the pipeline with an initiation interval of 1. The coding implementation shows how we proceed by a stride of tile row for each row and tile col for each column, and have a function called compute tiles to compute Mandlebrot values per pixel. To determine the optimal tile size, I experimented with various tile sizes on the x-y axis and observed both the BRAM and DSP utilization. From both figures, there is an exponential increase in the number of BRAMs as the tile size grows, and of DSPs respectively. I experimented with these tile sizes, checking both the synthesizability and the latency of the design for the final simulation. After synthesizing the design, the final tile size I decided on had 6x5 dimensions. While there are more optimal tile sizes, none of these were able to generate a bit stream. This size was optimal as it was hardware synthesizable and it could achieve a 176x simulated speedup on the maximum latency reported from the baseline. This also included other optimizations such as reducing the loop complexity and by dropping the data size of the types.
Let's look at some of the challenges with HLS coding. The first challenge is the complexity. We usually have to restructure our algorithm to apply different optimization pragmas. The second is a scalability challenge. We have to look whether there's a seamless integration between different PEs, different kernels. Then the third is we need a lot of manual tuning to get the most optimized HLS code. To tackle all this, we used ALO. ALO is a Python-based compiler that helps us in implementing hardware accelerators in a more modularized and composable manner. ALO provides a decoupled hardware customizations. This simply means that we can use the pragmas without even restructuring the code. Then it provides composable schedules, which helps us in seamless integration between different kernels. And it has the Python-based simplicity. This is how the ALO kernel looks like for our Mandelbrot computation set. It has two different kernels. One is the PE and the second is the Mandelbrot compute. The PE is responsible for all the major calculations, while the Mandelbrot compute calls the PE and then does a remap to different colors. As we can see, this is how the schedule looks like for the different optimizations that are being implemented on the ALO compute kernel. We can use enrolling, we can use array partitioning, we can do all these things without even changing the algorithm structure. Also, there's a primitive called split. We can do tiling. These are few of the primitives that ALO provides, and there are many more. As we can see, this Python code is equivalent to 250 lines of HLS code, which is rather more optimized compared to what a programmer could write. And it handles dependencies between different kernels. Now, let's look at some of the results that we got from ALO. This is the synthesis report that we got. And we could see that the latency that the synthesis report provided for ALO is less compared to what we got from our manual HLS coding. And this is what the resource constraints looks like. We have a far less resource constraint usage. We have less than negligible DRAM usage, lot lesser DSP usage, and a little bit of flip-flop and LUT usage. So all in all, we got a lower latency from ALO, lower resource usage, and the kernels that we develop can further be reusable. So these are few of the advantages that ALO provided.
Simulation time suggests large speedups for both our optimized and ALO designs. Unfortunately, we did not see that in practice. While our optimized design has a theoretical speedup of 98x, it only achieves a speedup of 27x on the FPGA. Because of this, we were suspicious of communication overhead, so we decided to measure this time by running just our DUT function on the FPGA. We found that this took 410 milliseconds, which was almost all of our execution time. Subtracting the communication times from both designs, we found that our Mandlebrot computation actually achieved a roughly 1600 times speedup, which is huge. This speedup does not come for free though. Our resource utilization increased quite a bit compared to the baseline design. However, all of our utilizations are below 60%, and since we're nowhere near the resource limit, this causes no issues.